Okay, so we continue talking about the it is set theory, and now with the addition to functions. Okay, so we talked about functions. We talked about compositions quite a bit. This is a one non-mathematical example, even though if you think of compositions, but really everything is mathematics. If you ask questions, if you recognize compositions, it is mathematics. It is if you do not recognize compositions, then you think it has nothing to do with mathematics. And then once again, if you don't ask yourself the questions, is it one-to-one onto questions like that, then it's not mathematics. So it's not knowing mathematics that's why it would not be about mathematics. You see what I'm saying? So it is your ability, your knowledge in mathematics that will allow you to recognize mathematics in different places where other people would. Okay, so an example of correspondence between senators and states, nobody would think about mathematics there unless they know the relevant mathematics. Okay, so you do from now on. Okay. So you can certainly think of other functions that deal with sets that non-numerical sets. Okay, so with compositions and on. In the meantime, so we look at bijections, or one-to-one onto functions. Literally, that if I say one-to-one onto in one word, it means that it made a function that is one-to-one and onto, right? So it's also known as a bijection, which is slightly shorter, but certainly not easy to pronounce. So so inverses is why we care, but let's review that the bijections that they came up. An example of using bijections that we it came up not too long time ago. It is the invention of numbers. So remember that example about a shepherd and his flock, and say sheep. And so naturally, prehistoric times, there are no numbers, there are no counting. Okay, so then what he did is, so remember the situation was in the morning he would take his flock to his herd into the pasture, and at the end he brings them back, but he never could be sure that he got them all back. Without counting, he's stuck. But he doesn't even know the word counting. So you could try to mark I don't know, with a color on the side of a sheep or something like that. But anyway, as the story goes, he would once again letting those cow or sheep out of the enclosure or whatever it was out, and then so for each. That's best I can do. A sheep of some kind. Okay, and then as the sheep passes through the gates, he would set aside a pebble. Okay, and then and so he at the end, once the pebble passed out through the gate, he has a pile of pebbles here, and the sheep is on the outside. So you can say that on the inside you have a pile of pebbles on the inside. On the outside, there's the herd. Okay, so and then on the way back, naturally he would go in the opposite direction, putting one pebble out of the pile that is the left from the morning, and until he runs out of either the pebbles or the sheep. So the point being, if you don't have all the pebbles thrown away, then it means that not all sheep came back, and you have to go look for them. And if it is just a few, you can actually take like 3 pebbles in your hand, and you go on, and once again you find one sheep, bring it back, throw another pebble away, and on and on. Okay, so as you can see, there's a one-to-one correspondence, a one-to-one onto function between the herd and pebbles. Okay, one-to-one and onto. Okay, so functions say from H to P. Okay, so then you can handle counting without knowing numbers, nor being able to count, period. So it's a pure common sense, and that's probably a good idea to think about it in these terms, not in terms of numbers. Okay, that helps you to think abstract and actually appreciate the set theory better, because numbers is like a shortcut that you learn in such an early age that you don't have to, so you don't question it, but really this is how really things work out if you apply nothing but common sense. Okay, and so that's what we're doing here. So so you can certainly ask what happens once its function is one-to-one onto. There is really nothing bijection. There is nothing to talk about because the functions are just so nice. But you certainly can remember if the shepherd is standing there and letting the sheep into the enclosure, and then he discovers that not all the pebbles have been thrown away, he says, what does he say? He says, well, I thought this function was supposed to be what? Well, actually, onto is the crucial part. So they're missing pebbles. That's if you have too many pebbles, then herd, then sheep, then the function is not onto, and that's how he knows that if the same function was onto in the beginning of the day, then at the end of the day it should be onto too. So if it is not, then there is a problem, and since assuming that nothing has happened to the pebbles, then something has happened to the sheep. Okay. So anyway, just an example, but really why we care about this is that when you take it to the next level and really take a broad look at where numbers come from, and then this is the definition: two sets well, you can put it in a number of ways. Have the same number of elements. Okay, so that's one way to put it. Have the same cardinality. In other words, is equipotent. If there is a bijection between them. Okay, so that's what the shepherd did. Established a one-to-one onto correspondence between herd and pebbles. Okay, so the notation is...
what word is that right there? Have the same what?
Cardinality.
Cardinality?
Yes. That's the word.
Then what is that last word?
Equipotent. Fancy words.
I
I gave you the first one. Is very good. Have the same number of elements is just fine. It is just misleading slightly because what if we deal with infinitely many, and we gonna. Okay, so then this first one will be incomplete and misleading. Number of elements implies a little bit that as if you have finitely many. Okay, so that's why the second one is probably the most popular, to say that two sets have the same cardinality if there is a bijection between them. And we're using this absolute value symbol to indicate that they have the same number of elements. Okay, so as you can see, sets, we can speak of all sets that we can imagine, and the definition applies because we just is there or is there not. bijection between them will give you the answer whether they have the same number of elements. Okay, and then we can actually say what that shepherd didn't, but we could now, based entirely on the set theory, we can now define numbers as a number of elements. Okay, so then in particular, we can say, we now can finally explain what we learned in first grade or whatever. So set X has n elements, f, so n an integer, positive integer.
You're explaining the thing right there?
Well, the definition is now done. The first one. I'm now trying to define based on this definition. I want to define such a simple concept as a set with n elements. Say 5 elements. What does it mean for a set to have 5 elements?
That's 5 elements.
Yeah. What does it mean?
It's got 5.
Well, we're trying to learn how to count. Imagine that shepherd was nobody to help, and he didn't go to school, and so there was no teacher to tell him how to count and where numbers come from. So he's inventing things. Okay, so that's what we're trying to do. So then he wanted to invent numbers so that he would apply them to sheep, to pebbles, and then to everything else, maybe fingers or stars, whatever, everything. And that works out if you do set theory. Okay, so smart shepherd. So well, why do you say you have you have a set of things, and you say that it has? How do you explain? How do you come up with the idea of numbers then? And that's how you have kind of a sample sets. Has the same, you have sample sets with, say, I don't know, 1, 2, n elements. Okay, so you start with your herd doesn't help you because it might vary in numbers, but that's why you might start with your fingers and you say then what does it have? What does it mean for a collection of anything, herd or whatever, to have 5 elements? Establish a bijection with your fingers. Okay, what does it mean for a collection of anything, or maybe this time cows, to be 10? Establish a connection with a bijection with your all fingers and both hands. Okay, and then you start maybe assigning. Later on, you might try to assign actual symbols to it, but early on, this is, you have to actually figure out what's going on there, and it is all based on these bijections. Okay, so that is very intuitive, and intuitive meaning that it is fully corresponds to what you have learned. So it is just we are starting from scratch, and that's a bit of a challenge, but we end up in the same place. There wouldn't be any point to invent something that and then turning everything upside down. So the counting, the numbering, will be still the same as we have learned early on. But where things become complicated, and that we really will be paying attention to most, is what if these sets are infinite. So the logic, and we are used to, well, first of all, remember there are a bunch of sets in mathematics, and you saw many sets that had infinitely many elements. I don't know, integers, real numbers, all of these. So we'll deal with that, and and we have to learn what's different about numbers that are finite numbers, finitely many elements in sets, and what if have infinitely many. Okay, so we'll deal with that later. Right now, we'll just stick to as far as the cardinality is concerned, only finite sizes of sets that we might want to deal with. But that's how when new concepts come up, you test them on the very simple situations first. And then just hope you don't make in the future assumptions. So for example, if you have two sets and you add them together and they're, well, what is this? X union Y. The cardinality, or the number of elements in the in the union of two sets. What can you say about it? When you count, remember first grade?
Yeah, dude.
Yeah, okay. Okay.
A little bit ago. But
Yeah, a while ago. Okay, so how many elements?
whatever.
What?
X and Y?
No. These are sets. So I understand what you're saying, and we can form the set of sets. We didn't get to that yet, but we will. Sets of sets. What happens? We did a little bit of that when we talked about equivalence relations. But this is just two sets, X and Y. The union of X and Y. How many elements does it have? Based on the number of elements X and Y. What?
It doesn't say, does it? I mean,
just it includes all elements in
Yeah.
that are included in.
What if we start counting?
The number of elements in X plus the number of elements in Y.
That's right. Provided. Yeah, it was supposed to be simple. I didn't mean it to be a trick question. So we have to make sure that what those sets they're disjoint. So we can add the two elements, the number of elements in of X and elements of Y, if they don't have elements in common. So common sense, once again, a common sense situation.
I thought like the X plus Y would be for an or statement.
No, it's literally. It is literally a number of elements is a number. So we're adding numbers. The number of elements. It is what it says. And the number of elements in the set is 1, 2, 3, 5, 20, n. Okay, so we have the definition of what does it mean for a set what it means for a set to have n elements. It simply means to have a bijection relation with element of that specific set over here. Okay, so we know what it means, and then we ask ourselves, does it still follow the common sense ideas about counting that we know? So it's how do we add numbers? That's how we add numbers by adding the whatever the manipulative you do in the first grade, like plastic things. You put them together, the 3 here, 5 there. Okay, you just pull them together, and you knew there were 3 there and 5 there. So, and then you just add them together, those two numbers. Incidentally, I remember reading about it that logic does not work out until later age. So, like if you're 5 and you know how many here and how many there, you pull them together. It's not obvious to the child that there is no more. It did not become bigger or smaller. Okay, so it is a development. It takes some development for the person to actually realize that yes, in between there is nothing has happened, and it is 3 and 5. It will be 8. There is nothing going on behind the scenes. And that's how we add. But since to make it more complicated, what if they might intersect? Then what do we do? Suppose they intersect, then what? Minus.
X intersection.
That's right. It's called the inclusion-exclusion principle. So it is easy to illustrate if you are willing to to accept this kind of visualization. So xy, okay, if I take the whole thing, then this is the union, right, x union y, and this one is the intersection. So in other words, if you just take the size of x and size of y, you double counting the intersection. So if you subtract, then you're fine. Okay, so kind of obvious, but it's good to write it down, and then whenever necessary, we might have to use it. Well, definitely, and then it would actually take a proof to really have a use of it. But I'm not gonna dwell on this. So until we get to infinities and deal with infinite sets, we don't really appreciate this. So because infinite sets, it means that these are some kind of algebra of infinities. So one infinity plus another infinity minus something that might be also another infinity. And you might remember from calculus that we are being very careful about doing algebra with infinities. What I want to do with bijections instead is talk about, as promised, about the inverses. So, well, inverses. So I don't see any. So it's by the way, once again, pre-calculus. Just like all the compositions 1 to 1 on to it mentioned in pre-calculus, but in just its setting is very elementary, and we are now taking it to an entirely different level. Okay, so anybody remembers the definition of inverse? So once again, we are in the setting of set theory, so we have a function from x to y. X is set, y is a set, f is any function. So any thoughts, or if you don't remember the definition, what do you remember about inverses?
Would it just be y to x?
Well, to begin with, okay, so the f inverse from y to x to begin with. So that's a good start to remember that it will go in the opposite direction. So if you remember calculus 1, it's usually from the x function from x, y is equal to f of x, and so there you have x and y axes, and that is good way to remember what's going on, is to keep x and y separate, and then if you go, your original function goes from x-axis to y-axis, don't change the symbols. Your inverse will be a function of y. So y equal x squared. Okay, the inverse, go the other way. What's the inverse? X equals square root of y. The only thing is that I need to fix the y equals x squared is not 1 to 1. So it's not a bijection. So we usually resolve it by changing the domain, remember? So we just ask x larger than or equal to 0 and y larger than or equal to 0. So my function will be simply this. Okay, so that's how it works out in calculus 1. And once again, I strongly suggest not to flip as change the name, just because now your variable, your independent variable used to be x and now it is y, does not change y to x. So the new function will be a function of y, which makes perfect sense. And once you write it, that's the second line over there, it becomes clear that, yeah, it just x's belong to elements of x capital, y's are elements of y capital, so we'll just stick to these two, and we have two functions living separate lives. So they interact how, and they interact, but how? By matching x's with x's and y's with y's, so you don't want to change names. So it is unfortunately what you see frequently in the pre-calculus. Instead you have what? Y equals square root of x as the inverse of y equals x squared. So anyway, we're not going to make that mistake, but we just proceed now from this to there might be many inverse functions, and we have an example on the right. So what else do we have to require from the inverse? what makes f inverse inverse? Well, just look on the right. How do you know they're inverses?
Same function, same graph.
Well, that's a fair way to say it. It's certainly an important observation is that it is, in fact, I plotted one graph, right? Because why not? So if we know that x is for function f, x is independent, y dependent. Okay, now we flipped it, and now y is the independent, and x dependent. So same graph. If I go with f, I go this way, right? And if I go with f inverse, I go backwards. That's all. But it's the same graph exactly. Okay. However, we didn't really for a while. Won't. I talked about graphs of functions in the context of set theory, so we have to do something else. So what is we'll get to graphs later, but for the time being, how do we define the inverse based on our example? What? Right. So you can discover that these two are inverses. You plug in one into the other. And we have a name for plugging in. Composition. So we define it through compositions. Okay, so we substitute, plug in, or compose one function with the other. Okay, so if you think about it, this is a diagrammatically how you do it. Well, we'll get to diagrams later. But f inverse of f of y. That's the substitution. I took my original function and substituted into, I'm sorry, this is supposed to be x over here, and substituted into the original. Just like, if this looks too complicated, look what's on the right. You can plug in x squared into y. How the substitution is literal, right? Literal. This y goes right there. That's the substitution. So y is equal to y is equal to x squared. So you replace y with x squared. Okay. So that's what the substitution is. You had y equal f of x, and now you have here x is equal to f inverse of y. Okay, so and the answer is, so I substituted, then what?
Reduce.
What?
Reduce. You have x squared, square root of that is just going to be x equals x.
Well, that would be, you don't want to say x equal x. No, this is equal to x. Okay, so it is what you discover on the right. You discover that indeed substituting one into the other gives you x equal x. But that's just an example. Right now we have two functions that seemingly have nothing to do with each other, and that's how we substitute one into the other. We're supposed to end up where we started. Okay, so think about this. If we have two sets, x and y, and we have a function f, like this. This is f, this is x, this is y equal f of x. Then the point is that we're supposed to be able to, whenever we go backwards, that's what f inverse is, we're supposed to end up not somewhere, but in this particular case, in the particular place, same where we started. So it makes complete the full circle. Okay, so this is not the whole thing. However, this only the half. What's the other half? That's right. So we substitute both ways. So you can make a circle in two ways, either starting with x, ending at x, or starting with y, ending with y. So I'm doing this f inverse of y is equal to y. Well, let's not forget the crucial part for all y in y. And here for all x in x. So that's what we require. The completion of the circle. So the first one is this. For the first one is this kind of. We're going to complete the circle from x to x. And then for the second one, we are completing, we're starting, this is the circle that we complete. So it's not the same thing. It is possible that things will break down. Okay, so that is the idea. It applies to these functions. That's not the definition, though. That's not the definition. If we want to be precise here, we would have to write it in a slightly more careful way. I mean, the trouble is with introducing notation without justifying it. That's we might be worried about, and using the. So the inverse. So we do not compute, unlike in calculus, we do not compute the inverse because there is no function to begin with, which means that our inverse will be defined by how? By nothing but by these two properties. If we define something by means of properties, it means that it's quite possible that there might be more than one. Just like with limits and everything else you see, this is a number that's supposed to satisfy this property. Okay, we neither know that it exists nor that it is unique if it does. Okay, so we are in the same place. We define no mention of anything, or no restrictions on f so far. So which means that, once again, it is possible that this doesn't work out, and we know that in general it does not. And then even if it does work out, we still have to demonstrate that there is only one inverse. Okay, so this is the plan of how we handle this. Precise definition, and then we have to demonstrate that the definition makes sense. So this is the definition. So given a function f from x to y, a function g from y to x is called an inverse of f. And then we just write what we had already there. I'm just use instead composition circles. So G circle F is equal to, well, of x is equal to x for all x in x. And secondly, F circle G of y is equal to y for all y in y. So that would be the strict definition of an inverse. Two conditions to be satisfied. Okay, and then once we start examining it, we might try to demonstrate that well, the two things that we worry about when we ask ourselves, is it well defined? And so always the same, defined. Existence and uniqueness. Okay, so well, we know roughly the answer to these. We know that it is unique, and we also know when the existence is satisfied. When is existence satisfied? When there is such a thing as the inverse?
When it's one-to-one.
When it is one-to-one onto. Okay, so it is what we kind of know. We just need to demonstrate it in the rigorous way of set theory. Okay, so let's start with existence. So that so that this is indeed works out. Okay, so which way? Well, let's just go. We will have a proof later in a more precise way. Let's just look at a few examples, just to demonstrate that indeed one-to-one onto is a requirement. So is required. So suppose f is not onto. Okay? Why is it a problem? So f works like this. So x and y, this is my f. So why we do know that it's not there should be no inverse. Can you see why not?
It's for all x, that's part of x.
No, so it could still, I could reverse the arrows. I have these arrows, I reverse them, and everything works out. It might. No, actually the second condition is the problem. The second condition is the problem because it's defined for every y, and it is the missing y's that creates a problem. Okay, so there is nothing to reverse. So the y, then what is g of, say, y naught? Okay, so suppose we start with, I should have started with that. We suppose that if it's not onto, then there is y naught in y, which is not covered. So f of x is not equal to y naught for all x and x, which is what I depicted that there, and then this is the problem area, y naught. There is some element in y which is not covered. Okay, so then y is a problem. Then the question becomes, what is the value of g of y naught? Okay. So it is not dictated by f because, as you can see, there is no arrow arriving from x to y naught. Okay. So how do we prove that? We would pretty much have to arrive to a contradiction, as I suggested, using property number 2. Okay. So okay, you see it? Well, just to substitute y naught into second property. So we'll look at second property, and we have f composition g of y naught is equal to y naught. Okay, and then which means that we can rewrite it as f of g of of y naught is equal to y naught. Okay, you see the problem already? There is a contradiction right there.
F never results in y naught.
That's right. So f can never, no matter what value of x you pick in x, f will never, its value f will never equal to y naught, and we found one. Okay, so f of some, say, x naught is equal to y naught, where x naught is equal to g of y naught. Okay, so we found a prototype for the corresponding value of x for y naught, which contradicts assumption. Right, so this is the assumption that we made, that it is not onto a missing element. We pick an element, and then we demonstrate that it is not possible for the condition number 2 to be satisfied. Okay? So, what else? Suppose f is not 1-to-1. Same, there is nothing for us to, we have so few theorems, so which means that every time we want to prove something, we go straight to the definition. There is really nothing. So if it is 1-to-1, we write the definition. So just like with onto, we use the definition, and now once again we're using the definition. So it means that it's not 1-to-1. Remember that picture? Well, let's have that picture. So once again we have a diagram to at least have an idea of why it cannot possibly work out. Say we have x1, x2, and then under f they go to the same value of, say, y1. Okay, so that's what not 1-to-1 means. Okay, When you have that picture, visualization of that idea, I write it out then from the definition. So there are x1, x2 in X with f of x1 equal to f of x2. Okay, so that's what it means for a function not to be one-to-one. So once again, we want to arrive to a contradiction. You can guess how the contradiction is going to go. Well, we used property number 2. Now we're going to use property number 1 to arrive to a contradiction once again. Right? So everything fits. Okay, so okay, the addition number 1. So once again, there is really no worry for us to do. What do we do with property number 1? We just plug it in, plug in x1 and x2 into my formula. So I have use property 1. I'm going to have so it is 1 second. So g of f of x is equal to x. So in particular, it will be true for x1, and it will be true for x2. And they are not. I'm sorry, I forgot this crucial part. So there are two distinct x1, x2 that bring that function f brings them to the same value of 1. Now, so I use 1 for x1 and for x2. You see a contradiction here? So once again, you can continue on and get rid of those circles and replace them with substitution in a bunch of parentheses. So I have g of f of x1 is equal to x1, and g of f of x2 is equal to x2. Okay? But, now what? How about we call this y1 once again? So they're taking, according to the picture on the right, f takes x1, x2 to y1. Okay? So we take that information and substitute. So we have then g of y1 is equal to x1, and g of y2 is equal to x2. Okay? So, I'm sorry, it's still y1 over here. Thank you. Okay? So you see the contradiction? That's right. So a contradiction because x1 is not equal to x2. So it's the same on the left-hand side. It's the same g of y1, but the outcome on the right is not the same. It was by assumption we would pick two distinct x1, x2. So that means that g is not a function. Okay. So we certainly can. That visualization is certainly should be very convincing if you do a few diagrams like that. But writing it out actually it does not take a lot of work. So another contradiction. And okay. So I call these examples, but what is let's state them in a more positive way. So what have we proven? Well, starting with number 1. So how do we put this analysis in the form of a theorem? The first one.
Function and its I'm just gonna say function and its inverse has to be 1-to-1 and onto.
No, it goes only one way. The assumption was about f not onto, and we were after a contradiction, which means that if there is the inverse, then f is onto. Okay, so these are the two things that we have proven. There is an inverse, then f is onto, and secondly, f is 1-to-1. Okay. So we'll We'll continue next time.